Welcome to the first of your pre-lecture videos in AA260 Thermodynamics. Hopefully you were watching this before the second lecture, as it will outline the theory needed to do the examples later in that class. Also remember to take notes, and if you have any questions on the material you see here, be sure to ask them in class. Also, if you want more information on the topics seen in these videos, the sections of the textbook are listed here at the beginning of each lecture. Thermodynamics is really just the study of energy and how energy moves, changes form, and is transferred between objects. It is based on two really big concepts that we will be seeing a lot throughout this course. These are the first and second laws of thermodynamics. The first law states that energy cannot be created or destroyed, conservation of energy, which you may have seen or heard of. The second law governs which direction that energy flows. This can take many forms, the most popular of which is the concept of entropy. We will be examining these laws further throughout the coming months. In thermodynamics, we have four fundamental dimensions: time, usually measured in seconds; length, usually measured in either meters or feet, depending on whether we are dealing with SI or US units; temperature, which can be measured in a number of different units, generally either Celsius or Fahrenheit, but could also be Kelvin or Rankine. If you've never heard of Rankine, it is simply the US version of Kelvin, the absolute temperature scale. More information on these in the next video, so stay tuned. And the fourth fundamental dimension is either mass or force. Mass is used in the SI system, generally measured in kilograms, whereas force is used in the US system, generally measured in pounds. Any other quantity is a combination of these fundamental quantities. For example, acceleration is a combination of length and time, as shown here. Other important quantities in thermodynamics are listed here. In the SI system, we have force, which is measured in newtons, which are equivalent to kilogram meters per second squared, breaking it down into the fundamental dimensions we just saw. Pressure is also important, measured in pascals. Energy, measured in joules, and power, measured in watts. Also, the SI system uses prefixes quite a bit to have more manageable numbers, so knowing the meaning of these prefixes is crucial. For the US system, unfortunately, there are generally not any easy conversions as shown in this table. Also, because force is a fundamental dimension, the mass becomes a derived quantity. The mass is the force divided by acceleration. The official unit of mass in the US system is the slug, although you also see pounds mass quite a bit. More on that later. You can see that slugs are analogous to kilograms in the SI system. If you take slugs times the acceleration units of feet per second squared, you get pounds, or mass times acceleration equals force. Pressure in the US system is generally measured in PSI, pounds per square inch. Note that these are not the fundamental units of pounds per square foot, although we see those too. And there are many other units for pressure as well, including bars, atmospheres, millimeters mercury, and others. In terms of energy, the standard units in the US system are the British thermal unit, or BTUs. Fundamental units for energy are equivalent to pounds feet. 1 BTU is equal to 778 pounds feet. In terms of the SI system, a BTU is slightly larger than a kilojoule. Power in the US system is usually measured in horsepower. 1 horsepower is 2,544 BTUs per hour, or 550 foot-pounds per second, or 746 kilowatts. And then finally, we have temperature. In terms of the absolute scales, 0 Kelvin is negative 273 Celsius, and 0 Rankine is negative 460 Fahrenheit. This is absolute zero in the US system. This table just shows conversions between the fundamental units in each system, SI and US. So going from meters to feet, kilograms to slugs, and newtons to pounds, and vice versa. I also have this, what I call a cheating conversion between kilograms and pounds. It is not a real conversion because one is mass while the other is technically force, but we can usually get away with it on the surface of the Earth anyway. Even though I just showed conversions between SI and US units, I don't actually want you to do this in this class. You'll be getting some questions in SI units and some questions in US units. Very few questions will have a mix of both. If you get a question in US units, I expect the answer and all of the work to also be in US units. I know that some students like to switch to SI units, do all the work, then convert back at the end, but I don't want you doing this. You will not receive full credit if you do it. In your future careers, especially if you work in this country, you will probably be dealing with US units. It is in your best interest to get used to them now. The relationship between mass and weight really comes down to Newton's law of gravitation. On the surface of the Earth, this reduces to the simple relationship that weight or force is equal to mass times gravity, where the acceleration due to gravity is either 9.81 meters per second squared in SI units or 32.2 feet per second squared in US units. So going from mass to weight, we simply multiply by g, and going from weight to mass, divide by g. So a 1 kilogram mass body will weigh 9.81 newtons, while a 200 Newton body has a mass of 20.4 kilograms. Similarly, a 10 slug body will weigh 322 pounds, and a 50-pound object has a mass of 1.55 slugs. This brings us to one of the more confusing aspects of the US system. We saw that the official units of mass are slugs. However, these are seldom used. More often, you see what I call shortcut units of pound mass as the units of mass. I do not consider these real units of mass because to get force from mass, you should multiply by g. However, this does not work for pounds mass. 1 pound mass is defined to be the mass of an object that weighs 1 pound. Therefore, to go from pounds mass to pounds force, you actually do nothing. If you were to multiply by g, 32.2, you would get the wrong answer. The way I deal with pounds mass is actually to treat it as a force, since it is equivalent. Also note that I hardly ever write lbf for pounds force. Pounds are a force by definition, so I find this redundant. Therefore, if you ever see lb or lbs, they are pounds force. If I ever mean pounds mass, it will say lbm. It is important to report your answer in a way that makes sense. You probably learned about significant figures in some of your science classes. Engineering takes a more real-world approach to significant figures. In real life, if you're trying to measure something, you can generally do it to about 3 sig figs. So that is pretty much what we use in engineering, regardless of what the scientific rules are. 2 sig figs is also acceptable, as is 4, but less than 2 is not really that accurate, so that is not good. I should also note that a number like 500 is fine. I don't count that as having only 1 sig fig. And more than 4 is very hard to achieve in real-life measurements, so also not great for engineering. So stick to reporting your answer to somewhere between 2 and 4 sig figs for every answer in this class. So now some basic definitions. A system is a quantity of matter or a region in space in which we are interested. Pretty much whatever we are interested in becomes our system. Everything else is the surroundings. A boundary separates our system from the surroundings. This can be a real physical boundary or an imaginary one, and can also be fixed or movable, depending on the situation. When it comes to the system, it can be either open or closed. This refers to the ability of mass to either come in or out of the system. If mass cannot cross the boundary, then the system is closed. If mass can cross the boundary, then the system is open. These two conditions are illustrated here. On top, we have a closed system. Our system, the green stuff, all stays in here. Whereas down here, there's an inlet, so stuff can come in and out. In either case, energy can cross the boundary. For example, if I have a flame down here, then some of that heat can go in and can heat up some of this green stuff. So a closed system can still have energy coming in or out, just not mass. A subset of a closed system is an isolated system, which is a closed system in which even energy cannot cross the boundary. Open systems are generally analyzed using a control volume approach, where a control boundary is set up and mass and energy is tracked as it flows into and out of the surface. A property is any characteristic of a system. These are things like pressure, temperature, velocity, energy, etc. Properties are generally divided into two categories. Intensive properties do not depend on the amount of matter involved in the system. These are things like velocity, density, etc. Extensive properties, on the other hand, do depend on the amount of stuff in the system. These are things like mass, momentum, energy, and so on. Another class of properties are called specific properties. These are extensive properties, but per unit mass. We will see some of these next class, and more as the class progresses. The system is completely defined by the state of the system. The state is basically the collection of properties of the system at the current moment. What is the pressure, temperature, etc. If the state of the system is not changing, then the system is in equilibrium. There are many types of equilibrium. Thermal equilibrium is if the temperature is not changing. Mechanical equilibrium is if the pressure at each point is not changing in time. Phase equilibrium is if there are no changes in phase occurring. Chemical equilibrium is if the chemical composition of every part of the system is not changing. And there are a few others as well that we will not get into. The most important for this class is called thermal equilibrium, which is basically just the combination of all four of these previous equilibriums. A process is anything that changes the state of the system. The system begins in some initial state, temperature, pressure, etc., then ends in a final state with possibly different values of temperature, pressure, etc. The process defines how these properties change between initial and final states, as well as any interactions with the surroundings, if possible. The process path is the series of states through which the system goes through from initial to final. Then if the initial and final states are the same, the process is called cyclic, and this series of states is called a cycle. As an example of these concepts, shown down here, using the gas in a piston cylinder device as my system, we start out at some volume V1, so piston over here on the right, also have some pressure at that point. Pistons then move to the left. So my system is now at some lower volume, V2, and some higher pressure, where these are shown on this pressure volume graph here. So starting out state 1, then higher pressure, higher volume, going to state 2, and have this process path for every pressure and volume as this piston is moved to the left. Then if I wanted to move my piston back to its initial state, we'd end up at the same volume, V1. And if we end up at the same pressure as well, then this process would be cyclic. It doesn't necessarily have to follow the same path on its way back. It could. So I could have this process path to go back to state 1, or I could have a different one, maybe come down here, then go back, and then back up here. But as long as I end up back at the same state, same pressure, same volume, same everything else, then this process would be cyclic. A quasi-static process is one that changes very slowly, so slowly, in fact, that the system can be approximated as being in equilibrium throughout the entire process. There are a few other approximations of processes that we use in this course. An isothermal process is one in which the temperature does not change. An isobaric process is one in which the pressure does not change. An isochoric or isometric process is one in which the specific volume or density does not change. And finally, a steady flow process is one in which the state of the system does not change in time. So steady refers to time dependence. The system can have different properties at different locations, but these do not change in time. The last thing to deal with today is the notation used in this class and in the textbook. Many concepts sound the same in thermodynamics, but there may be some small but important differences. Anything per unit mass, usually denoted as a specific property, are denoted by lowercase symbols. For example, if uppercase U is the energy, then the specific energy, or energy per unit mass, is lowercase u, or lowercase u is equal to uppercase U divided by the mass m. There are also a lot of variables denoted by V. The textbook uses capital V for velocity, whereas I use lowercase v for velocity. The textbook uses this weird looking V for volume, whereas I use normal uppercase V for volume. Then specific volume is a lowercase weird V in the textbook. I actually use Greek letter nu, which looks a lot like a lowercase v, but note the slight difference, especially at the end. This little curly on lowercase v or velocity, that is not there on specific volume. The only other big difference between my notation and that of the textbook is for the universal ideal gas constant, usually denoted by R. This is what you probably recognize as 8.314 joules per mole Kelvin. There are a few ways to deal with the ideal gas law. We will see this later in this course, but there are a few different versions of the ideal gas constant. In this class, we will use R for a different version of the ideal gas constant, and therefore the textbook uses R sub U as its universal value of R. I use this fancy looking R as the same value of 8.314. So that is it for your first pre-lecture video for AA 260. Hopefully you have taken any necessary notes, and if you have any questions on the material in this video or on anything else, please ask them at the beginning of class. I will hopefully see you then.